Good afternoon. It's my great privilege and honor as director of the Institute of Mathematics to open this edition, 7th edition of the Professor Stanisława Łojasiewicz lecture. Let me welcome our guest of the day, I would say guest of the year, first of all. Then welcome correctors, Professor Stanisław Kistryn and Professor Armen Edigarian. Welcome the Dean and Vice Deans. Welcome all professors and students. We are happy to have you here in this room. And, well, I think that first I should recall some history. This is the 7th edition of this Professor Łojasiewicz lecture, and it was a really fantastic series of speakers. It was first Shitung Yao, then Richard Hamilton, then Bernard Malgrange, then Neil Trudinger, then Fernando Coda Marquez, and the last one, Noga Alon. And this, I shall already fantastic series now extend Professor Artur Avila. It would be boring for him to explain who he is, just Field medalist, and it explains everything almost. On the other hand, I would say it is just a mathematician who wants to share some piece of his knowledge with us, and we are waiting for it. Well, we were trying to invite him here for months, and at last, Dominik Kwietniak succeeded. Thank you, Dominik. Thank you, Dominik. And then Professor Dominik Kwietniak is the chairman of the session. Thank you and welcome.
Thank you very much. I think I can be heard without a microphone. So let me just add to this great introduction that I think that now Brazilian mathematicians are leading on the list of the Łojasiewicz lecturers, because it's a second out of 7 Brazilian mathematicians who will present a lecture here. Second from IMPA, I also think. And now the title of the lecture, so it's one frequency, Schrödinger operators, and almost reducibility conjecture. And if I'm not mistaken, that the stage is yours, Artur, please.
Okay, thank you. Thanks, Dominik. I'm happy to be here, and it's my first time in Krakow and in Poland, and I'm finding a very lovely experience. I hope it will continue in the next few days. So I'm going to talk about something that is mostly, I don't know how far I get, but involves many things that have been published already and some things that are not available just because it's taking a long time. But so I'm talking about this general subject of one-frequency Schrödinger operators. So I introduce this, and then I just quickly get to the kind of dynamical system that is associated and what's the problems that are related, and relate to Lyapunov exponents and the concept of reducibility, and how this concept of almost reducibility that's kind of being explored more recently allows to get the kind of information to really settle some of the fundamental problems for the original spectral setup. So anyway, let me fix conditions. So a Schrödinger operator on the discrete one-dimensional lattice. So we are going to consider something that's on L2 of Z. And there will be an operator acting here that you have this form. So it acts on a sequence U. So what's the nth element of the sequence? It is computed by doing this procedure that's essentially a discrete Laplacian. So you take the near neighbors and do this interaction. And then you add a diagonal term, which will have the form v of n alpha, let us say. So in general, you add a few more terms, but let's write like this: v of n alpha plus times un. So that's the diagonal interaction. So if you think in terms of matrices, so this could be imagined just like an infinite matrices, which have ones just off diagonal. And here you put, here, let me just mention. So v is an analytic function on the circle alpha will be taken here. Sometimes you make some periodic approximation, so it could be a rational number, but it will be an irrational number here most of the time. So the circle here. So it's a one periodic function, the real line. And analytic. So that's the setup that I'm choosing. So here you're going to have terms somewhere there be v of 0, v of alpha, v of 2 alpha, and v of minus alpha, and so on. So you get this. So you have this particular formula. What is it supposed to code? So this comes supposed to model certain problems in physics. So what you're going to be doing with this operator, so this is a linear operator, but with respect to the problem, so this is what's behind some quantum dynamics, which is obtained when you're going to take, you exponentiate it like this. So this leads to some evolution, unitary evolution of some state. So you have a state here that would be a unit vector in L2 of z. So it codes some state of the system, so it gives some kind of complex amplitude that then, so you have this lattice, and with this complex amplitude, you basically kind of get information about probability of locating a particle in some place. So that's how you could interpret, and then you do this quantum evolution of this dynamics of this state. So that's kind of this unitary evolution of this unit vector. And in order to understand this, what's the properties of this evolution, in the end, you need to understand well the spectral properties of this operator, right? So let me mention a few possibilities. Let us suppose that, for instance, there is no such term, right? It is so that there is just this part, so that there's no, this is called the potential here, usually. So if there's no potential, then it's known that the evolution is just kind of, you start with any state, and it kind of dissipates, it kind of moves around to infinity, like it becomes more and more dispersed. So you start finding the particle more or less everywhere, anywhere, and it kind of moves, in a sense, the location that you could expect to find the particle is moving to infinity. So you compute the momentum of your state. So that so there's a large probability to find it very far away, even if it starts localized in a particular place. On the other hand, there are some other situations that could arise. So that's kind of, you'd need to prove that it does arise, which would be in the case of where, let us say, that this term would not exist. So this would supposed to model the situation where this term is very large. So because the spectral properties, basically the qualitative, don't change if you multiply everything by a constant. So getting a very large constant here is more or less similar to have a very small constant here. And let's assume that this term didn't exist in a kind of limit situation. Then kind of you should start kind of localize it in a point. It's just a diagonal operator this time, so it just stays at the same place. So you could imagine a small variation, and there is this notion of localization where a particle is initially located more or less precisely in some part of your space, so somewhere, and with time, as time passes, it still is more or less located in this part. So there's a large probability to finding it somewhere fixed. Now, in a compact path. Now, there is so this basic possibilities like transport and localization.
Please change the chalk. Maybe the chalk which is on the table is a bit better, because this seems to open.
Okay.
Better?
Okay. It's, for me, it's basically the same, but maybe you see better. So I'm giving just two alternatives. So transport means the particle basically is moving away fast. There's this notion of fast transport, ballistic transport. It goes away unimpeded by the potential, so as fast as possible. And localization means that it's kind of basically not moving. So there's a kind of an alternative here. And I don't want to get into the theorems that get there, but there is some direct connection to a certain extent between the concepts of about the basic spectral properties of this operator and the dynamic properties of this evolution. So let me just mention then what's the spectral property here. It is, let's see. It doesn't go up. Okay, let me use a different one, otherwise don't see. So the spectrum of this operator, it's easy to see, well, that it's a compact, so spectrum is what? It's a compact, perfect set, so you shouldn't think of the spectrum, the potential here is bounded. So this is a bounded operator, so you shouldn't think of kind of eigenvalues going to infinity. You shouldn't think of isolated eigenvalues either, because it's perfect. It's in some kind of fixed part of the space of R. So it's a compact perfect set. And it is often, so just that you don't get a wrong idea, it's often, and almost always would expect, often a Cantor set. So it's very difficult to prove, usually. So it's often a Cantor set. And let me say also that often has positive measure. So there are exceptions. So that's, you imagine some kind of a fat Cantor set. And what you can, but this is just kind of topological and basic information about the spectrum. So you're seeing the spectrum as a set, what kind of set it is. But from the point of, to understand the behavior of this operator, you're interested on how you see the decomposition of the spectrum. So you decompose this, so you have a spectral measure associated, according to the spectral theorem. So instead of having a set, you get this measure. And then there is the decomposition into the basic parts that are, there is an absolute continuous part, just by general continuous. It can be singular continuous. And there is atomic part. So this corresponds to eigenvalues. But not everything is in this kind of infinite dimensional setting. You don't only have eigenvalues. You can have these other things. And basically, what this is related with respect to that dynamics is that this is related to fast transport. So when the particle moves as fast as if it was not obstructed by the potential, as if the potential was 0 here. And atomic part is related to localization, because it's diagonalized, and it's like in the situation that I mentioned. So this localization, or in a sense, so the dynamics is easy to describe. The quantum dynamics is almost periodic. So if it was just, if there was only eigenvalues, it should have this. If there was only absolute continuous spectrum, then the particle would move away. But in general, of course, you can have everything. And this part here is kind of intermediate and mysterious. Then the precise properties of how the particle evolves become kind of more subtle, and it will depend a lot on other things. It's not kind of, there is some information that you get, but then you need further analysis, so it's kind of more complicated. So the easiest to describe are the first and the third case, the most spread out and the most concentrated from the point of view of spectral measure. Okay, so that's kind of for the spectral theory, and let me just mention what kind of goal that eventually a long theory has led to is, I state, one kind of theorem to know what kind of things eventually you prove. Let me give, maybe it's convenient to have one example, because so far it's too abstract. So example here that people might find many if they start looking at papers about this after the lecture. So basic example is the almost mature operator. With what you get if you just write for V, you write a 2. It's a family of operators. I should have introduced one more parameter, so V of x is equal to 2 lambda cosine of 2 pi, let's say, theta plus x. Okay, so there's a parameter here that's being introduced. So there is already one parameter there that was alpha. Now, once I fix this shape, you also get a parameter lambda that's called coupling constant. So this frequency, this coupling constant, that can be small or large, and theta, it will play very little role here, but it's called the phase. But it is important for some subtle issues related to localization. So it's not an unimportant parameter, but it should more or less disappear in this lecture. So, there is something that depends on a few parameters, and then let me just mention how far goes our understanding with respect to things that I already said. You know that in this case, the spectrum is a Cantor set. So the coupling is non-vanishing. Let's suppose that's positive. Spectrum is a Cantor set. This is was a conjecture known as the 10 Martini problem. Became a theorem. It has measure, so the measure of the spectrum is known exactly, is 4 minus 4 lambda. So it's equal to 0 for exactly for lambda equals 1, which is called the critical point. So there is kind of this special parameter where the spectrum has exactly measure 0. And for the colored subcritical, so lambda less than 1, so subcritical, you have purely absolute continuous spectrum. And for lambda larger than 1, you have, so this is supercritical. You have pure point spectrum, so you only have eigenvalues. And let's say for critical point, you have singular continuous spectrum. Let me say here, pure point spectrum for almost every alpha and theta. And here you have singular continuous for almost every alpha and theta. I can be a little bit more precise, but I want to be. Okay, so you see then for what I'm saying is that for small coupling, so it mimics what I was saying. If it prevails this part here, so the potential is small, so you pretend that it didn't exist in my original thing. So in fact, as long as this parameter is below 1, you get kind of this kind of almost like the free case. So you get pure AC spectrum. If you go above the critical point, you immediately get pure point spectrum. So there is a sharp transition, which is called the metal insulator transition, which was studied by many people. Okay, so you have this kind of very basic information. There are some kind of special features of this, in particular responsible for us being able to compute this kind of, it's very weird that you have a complicated set. This is not an interval or a finite union of intervals. We are talking about a complicated Cantor set with kind of a very complicated structure. I don't have the drawings, but it is actually complicated. It's not, and somehow you put together all this Cantor set and you get a very simple expression. So what's behind the possibility to compute so precisely this? So there are some kind of very interesting computational phenomena related to this. There is also some important symmetry that's particular of the system. It's some kind of self-duality that relates large couplings and small couplings for this operator. So that there is a so-called Aubry duality that allows to understand why if you have some kind of pure point spectrum for large coupling, you end up with pure AC spectrum for small coupling. And so everything connects, very particular in this operator. And on top of this, I should mention that it has some special relevance for physics, the almost match operator, because it is it was as a specific model that with this shape, which is called, they say for Bloch electron in magnetic field, so that it comes from pairs in the torus. And it has been linked in the 80s to quantum Hall effect. And there are even some, I'm not specialist at this physical side, but nowadays there are people that make experiments. So there are fractal sets that are associated to this. There are people that make experiments with graphene. So there is some kind of new things that people find out. And that this has been used to kind of detect this kind of fractal sets in sort of nature. So really, the things, the kind of features that you discover related to this operator that have been mathematically described, in the end, they seem to really code something. But this is not going to be important for us because what's interesting, the mathematical theory that behind this is extremely interesting itself, so especially the connection to dynamical systems that I will make in a moment. Okay, so let's see if this one goes up or I keep. Yeah, it somehow didn't choose well how to start. So let's see. So this one stays here because it was the last one that I wrote. I move here. This will be kind of disappear. Right. Okay. So how do you then? So now let's see a little bit of the theory of this kind of operators. You have the. How do you approach this? So you have an equation that is, which I erased, so that you'd like to look at the eigenvalue equation. That's the kind of first immediate thing that you could try to see. Let's see how would an eigenvalue look like. And that was stupid because immediately I could have the equation here so that you write equals E U N. So let's say that you write this. So you rearrange the things and you get an equation here involving UN plus 1, UN minus 1, and UN. And you can write, so it's a second order difference equation. I rewrite it here in the following way. So UN plus 1, UN. You can apply this matrix here times UN minus 1. So you get this. So if you start somewhere, so there's some original freedom, you choose two guys like this, and then you apply this matrix here. Let's write this matrix for A. So let's write for the matrix E minus V of X minus 1, 1, 0. You write A of X. And then you apply here A of 0, and you get the next one. And then you apply A of alpha, and you get the next one, and A of 2 alpha. And then you generate whatever you wanted here. Eventually to get the un plus 1 un. Here you apply until A and alpha, let's say. Right? So, yes, I hope. This is some simple procedure. And so understanding the behavior of this would be understanding this matrix product. And then you do it backwards as well with taking inverse and so on. So basically, if you understand how to take those products of matrices, everything becomes fine. So let me say that you look at this equation. So of course, in the end, if it's an actual eigenvalue, you're going to have some decay property so that it will be a function in L2. So that it should kind of decay in the future and decay in the past sufficiently fast. But somehow it's useful to understand this equation even with solutions that are kind of not decaying. Like this kind of the understanding of the behavior of the solutions will maybe allow you to detect this absolute continuous spectrum and distinguish from singular continuous spectrum and so on. So understanding this equation turns out to be important in all cases, even for non-decaying solutions. So so you'd like to understand this kind of matrix product. And let's see, I wrote this so that I don't need to do this all the time. Go here. So our you do this. So how do you call this? So then you write a dynamical system associated to this, which has the form. There are two variables, x and y. So the first variable moves, so this x belongs to the circle, let's say, and just moves by alpha. And y, it moves to a of x times y. And here y is something that you're acting on. So originally you could imagine the space of such vectors. So y might be in R2, but you could let it act elsewhere. Like one convenient choice, look at projectivization here. So then instead of having a two-dimensional space, you have just the circle, right? So but then something where a matrix like this, which belong to SL2 are, by the way, okay, so you have this kind of system. And then when you evolve the system, so you iterate many times. So let's call this alpha A. It acts on xy by this. So if you apply the system many times, so it is acting on x and y, and then you can apply again and again to use it as a dynamical system. So you apply many times. So take nth power of this. Then you move x to x plus n alpha, and y exactly to a matrix product like that. So exactly something like that you got here if you had put, let's put un minus 1. And here it becomes un minus 1 alpha. Yeah, so it gets exactly like this. So basically, if you understand this kind of iteration, so this dynamical system, you are going to get a lot of information about this. So one point is that it's not just one dynamical system, one iteration that you need to understand, because here this parameter is free here. It could be any real number, and you're mostly interested in the spectrum, but this gives you a potentially positive measure set of parameters to understand. So you get associated then to spectral properties of H. It's connected to dynamical properties of a one-parameter family indexed by this exactly energy E family of dynamical systems. And this kind of dynamical system, due to its special form with this kind of matrix, fibered action by matrix, we call it cocycles. And more precisely, because of the initial part, it's one-frequency cocycles that you should say. But let's call it cocycles here. So if understanding this relates to getting there. So let me mention some connection that you need. For instance, one possibility that you get from this matrix is that let's suppose that V was 0, so that there is no term, so the matrix was constant. Then it's always the same matrix, so you're taking just a power of a fixed matrix. And basically there is three possibilities. There is hyperbolic. Well, let's just focus on here, so that there is one eigenvalue bigger than 1 in absolute value and one smaller than 1. And the matrix grows exponentially fast, right? So it leads to exponential growth. Or you could have some kind of bounded product, not bounded, but elliptic, which have two distinct complex conjugate eigenvalues, elliptic behavior, which leads to bounded behavior. And then there's one intermediate that's kind of border behavior that it can be parabolic. It can be like 1, 1, 0, 1. So this relates to the trace of the matrix, kind of pretty obvious. So you have this kind of hyperbolic. If you start from a hyperbolic situation, and one first information, if you start from a hyperbolic situation and you move, it's very easy to compute in the case of v equals 0 when this happens, it's outside minus 2, 2. So let's see. So for the case of constants, it's like E does not belong to minus 2, 2. And if you kind of now have a very small potential, just kind of telling about something that could happen, then this kind of basic property of exponential growth will be still satisfied. What you're going to have, you are going to have an exponential growth of your matrix co-cycle. And in fact, it's very similar to the situation. When you have a fixed matrix and you start iteration, that there is the eigenspace associated to the smallest eigenvalue that will be contracted exponentially fast, while the eigenspace associated to the expanding, the largest eigenvalue expanded exponentially fast. If you have the situation where the matrix depends on the point, but you are perturbing from the situation, what you get is a situation that you have some kind of stable and unstable space, so eigenspace, but not eigenspace, but they replace this concept, so that for each x, you're going to have one space u of x and another space es of x, and their sum is R2. Okay, so there's this splitting, which is going to be which will be regular and so on in this situation, but you're depending on the point, and vectors that are here, they are going to be contracted exponentially fast, and vectors that are here are going to be expanded exponentially fast. So it gives you a certain information, but it gives also some information, because a vector, it always grows, like as a vector is in the stable or the unstable direction, but cannot be in both. So it's possible that a vector, if you iterate, becomes small, exponentially fast, but then when you iterate in the other direction, it becomes large, also exponentially fast. So in the end, this is kind of not related to find an actual eigenvalue, and in fact, you can see that this kind of hyperbolic behavior, or uniformly hyperbolic behavior, leads to that you actually cannot have, you are so far from being, have a bounded solution, decaying solution, but not even bounded or not even slowly growing, that this means that the energy that associated, means that you are out of the spectrum. So it's not kind of very important for us when you get this. This is the first information. If you kind of get this kind of basic behavior for this kind of matrix co-cycle, it relates to some kind of spectral property, but some kind of trivial spectral property, like this. Okay, so you have this example of information. And now, what may happen is that there exists such a thing as non-uniform hyperbolicity. Which is the situation where there is exponential growth. There exists exponential growth in average. It's not uniform. So you called it in terms of some kind of Lyapunov exponent which called, let's call this product here an of x. So is a limit here, the asymptotic exponential growth is lim 1m integral log the norm of the matrix. So it grows, to get this kind of positive, you need this, to be growing exponentially fast, this bigger than 0. So in average, with respect to x, the mates that you're getting are growing pretty fast. So you have this, so that's kind of similar to the situation that was just for a single matrix. But it may happen that this happens non-uniformly, and what happens that you still have so-called splitting still exists, but it's only measurable. So it may happen, so in general the splitting are two spaces that don't coincide, but it may happen that, let's say in some very small set, they could be equal. So there is it allows for exceptional EU equals ES. And what does it mean, EU equals ES? Means that you contract in the future when you iterate forward, and you contract in the past when you iterate in back. And this leads to an eigenvalue. Okay? So in a sense, a different connection that usually, so the moral of the story is that if the Lyapunov exponent is positive and you're not uniformly hyperbolic, that's what's called because otherwise you're out of the spectrum. So-called non-uniform hyperbolicity is linked to point spectrum. But this kind of is a little bit complicated. Let me write it a little bit like this. But it's related to point spectrum. And that's behind many of things that I mentioned about the almost mature operator. OK, so you get this kind of nice get a new one. So you get this. So what about a C spectrum? So now you have something that's very interesting, that is the related now to concept of reducibility. So another dynamical concept comes in. Let me just have an idea of time. Yes, going fast. Another concept is the following. So now an important part of dynamics theory that kind of is so-called KEM theory. So let me introduce, because most people here are not dynamicists. So it's a very important part of dynamical system that just to get an idea of the importance, it starts, so it originates, so those three persons are Kolmogorov, Arnold, and Moser. They are interested on, for instance, Kolmogorov originally, you take a mechanical system, let us say, and you try to show that there is some kind of regular behavior, quasi-periodic behavior. So some very simple mechanical systems, for instance, the two-body problem, so where you would have just a planet going around the sun, but in fact both interact. But you have this kind of elliptic objects that you have when you have just interaction between one particle and another particle under Newton gravitational law. And you get something that's called quasi-periodic motion, so it's an integral system. So everybody learns in school. That's something that you can describe. So that's nice. And we also know that people don't know what to do basically very well if you already have three particles interacting. So that's three-body problem. It's very difficult. You can try to understand if you make some progress if you have two particles, and then you add just a very small, tiny one. So imagine that you're perturbing from a situation that you understand well. So you are starting from kind of integrable situation, let us say, and then you consider in some limits, something that's close to what's perfectly described, but it's a variation. Does it kind of become completely different and nothing saves? So for that has been a long problem, so many people contributed and discovery that it's complicated due to Poincaré, for instance, is kind of famous. But then Kolmogorov said that, well, I have a theory that he started that says that actually this kind of nice motions, that kind of quasi-periodic motions, they have a tendency to persist when you perturb. So KM theory is about, in a sense, persistence, the trend to persist of quasi-periodic motion. So let me give you one example related to this. Let me propose that this variable here will be projective. So I get, instead of R2, I am going to get a circle. So now our space was one torus, and then you add a new a circle on top of this, so you get a two torus topologically. So that's our space there. Dynamics in the first variable is just turning. Let's start from the easy situation where A is constant. It could be a rotation matrix, but a constant rotation matrix. You put two of them together, you get a transformation of the torus that up to a trivial coordinate change is just a translation of the torus. So if I make the torus square, so by identification this, it's just it moves always in the same direction, or you're kind of turning in kind of very boring way. So orbits just move like this, so get this kind of quasi-periodic motion. Exceptionally, it can be periodic, but normally it will be quasi-periodic. So this is one of the objects that KM theory likes to work with. And then what you're going to say is that when you perturb the dynamics by introducing kind of making this potential non-trivial, you are perturbing this dynamical system that's starting from a favorable kind. You start from kind of one of those nice kinds. And the conclusion is that, so the theory is used to say that after perturbation, so for small, there is a trend to keep quasi-periodic motion. This would be what does it mean to keep quasi-periodic motion? Well, in the highest, most strict sense, it would mean that after change of coordinates, so I have this, it is a diffeomorphism of the two torus that you're applying. You could make a change of coordinates by diffeomorphism. Usually you restrict it because it's natural to consider a fibrate situation here. But up to a change of coordinates, so you change coordinates, and you get a new torus. So you had changed dynamics, so here you had some kind of rigid translation or rotation. Let's write make a round things. Rotation plus perturbation. And now you change coordinates. And now you get again a rotation, rigid rotation. So if you have this kind of, if this happens, that you can change and just get again a rotation, this is called reducibility in this setting. And so what I'm saying is that KM theory says that many things with small potential, as long as the parameters, the coupling or whatever, is not very large, many things are going to be reducible. So that's kind of direct application of KM. Now, KM has, it's well known to have very subtle issues because how to prove this is something that in most settings not generally valid, and you need to make several assumptions of arithmetic nature about what you're doing. So like not all quasi-periodic motion tends to persist, but only those that are associated to a translation. So here is a translation vector. In those coordinates, you get xy goes to x plus alpha, y plus beta, right? If alpha and beta were rational, for instance, or even rationally related, you get some kind of very rigid trajectory that's kind of extremely unstable. So this you don't expect to persist. What persists is that when alpha and beta generate some kind of very rational direction. So which means which is coded in a kind of notion of Diophantine approximation, saying that alpha and beta are very non-Diophantine. Let's say, let me just do the condition for alpha. For instance, there is a joint condition for alpha and beta. But one usual condition that appears, the Diophantine condition, says alpha is not very rational. So a rational number, you multiply by a certain number, you get an integer. So a guy that's very rational, when you multiply by an integer, whatever it is, non-zero. And you don't get an integer. So it's not zero, this. But it's actually far from zero by general theorems. It can be close to zero, but it's not very close to zero. Usually you state in some kind of form like this. So there is some kind of power law possible approximation. That's it. And then there are theorems saying that most numbers satisfy a condition like this, almost every number, in fact. If you fix constants here, you're going to have a positive measure of numbers. So you have this large set. And that's the kind of motion that KM guarantees persistence. But I'm warning that then it's delicate, and you're always talking about some kind of positive measure. In particular, you're usually not talking about open sets of conditions. So somehow delicate to kind of put your hands on this thing, but that's what you actually can do. So there is this important theory, and that's kind of behind this. Let me mention one theorem then that appears in the, so let's see. This is basically my theorem of Rafael Krikorian, and maybe an addendum with Fayad, Bassam Fayad. But one theorem that says, which is extremely general, is that if V is analytic, alpha is Diophantine, right? Then for almost every energy, you either have the Lyapunov exponent is positive, or you have this kind of KM phenomenon. You have reducibility. So that's, in this form is with Fayad, because there is a condition here. So, so this is a very interesting result for that gives you some information. So already from the point of view for almost every parameter, let's fix this is also almost every parameter. You have a separation in between this kind of positive Lyapunov exponent, which tends to which is kind of compatible and pretty connected with eigenvalues. So one of the behaviors there, and the other behavior that's reducibility, that means that you basically reduce to the situation that was with constant coefficients, you get bounded matrix products, and in fact, it's connected to AC spectrum, usually. Well, indeed. So, so you have this general theorem that's proved by a technique called renormalization, plus KM theory, standard KM theory, or more standard KM theory. So renormalization, so the new technique that was implemented here with some kind of parameter exclusion that from somewhere appears some almost every condition is dealt with by this stuff. So this is one theorem, but this is kind of old theorem, so it was proved in 2003. Why I was very happy with this theorem, because from the point of view of dynamic systems, it's very normal to, there is a need to exclude something. So I said almost every energy. And of course, you cannot do for every energy. Sometimes there is a zero measure exceptional set that can be even a little bit large, which exists. And you have no hope to having, in principle, more than that. But still, you should be more precise, because a zero measure set could carry a lot of spectral information, because spectral measure is not Lebesgue measure. So the spectral measure can kind of be concerned with the exceptions of this theorem. So while it's a good theorem from dynamics perspective, in order to derive certain or special spectral consequence, you really would not like to kind of exclude to be so abrupt to just exclude some zero measure set and say it's small. It's not. You have to justify why it. You'd have to justify why it would be small. So that's the state at this point. And so you'd like to understand a little bit better all energies. And now you have this difficulty that this concept of reducibility is a little bit flimsy. As long as you have reducibility, it's going to be talking about positive measure sets. And to avoid this, so there's a concept that kind of comes in, which is related to title of talk. So almost reducibility. Right. So what's reducibility? It means that your system is basically constant. It's like a given without this V analytic function and so on. Your matrix is always the same. And you say you can put in your situation where you basically have a constant matrix by one change of coordinates. But what happens sometimes and is that how do you produce this kind of change of coordinates? Usually the KM scheme is kind of based on usually iterative Newton scheme, so that's how it's born. Then there are variations due to implementation by Nash and things like this that made it apply in other situations. But basically, there is a sequence of approximations of this change of coordinates that gets you close to constant. So in practice, you have a system kind of alpha A, and you start kind of trying to make it close to become a constant, but you get a sequence of changes of coordinates that gets it closer and closer to constant. And this gets close to, and this getting closer to constants. And getting this, taking the limit here, you get a change of coordinate that gets you to constants. What may happen, and does happen, is that sometimes, due to the arithmetic, so this was discovered in applying KM theorem, so people are doing KM theorem, trying to apply this, and they could construct the change of coordinates in a much larger, with much larger scope than originally you could expect from KM theorem. You're getting the BNs, you're getting this going to close to constant, but the BNs will diverge. So you may get this, but with possibly diverging Bn. So one place particularly where this makes an appears is was in work of Akan Eliasson. So he got a general situation where he could get a generally implement the KM scheme and everything worked except for this convergence of Bn. So define almost reducibility. So let's make this. Define almost reducibility as saying that you can make this change of coordinates, and this doesn't need to be by a usual KM scheme, by some way that you're smart and found this change of coordinates with this Bn possibly diverging. Okay, so so that's the definition of almost reducibility. Now, are there obstructions to almost reducibility? Yes. And let me say that everything here is in analytic sense. Everything that I say here is in analytic sense. Okay, obstruction to almost reducibility. So this matrix here that you're getting, usually unless you're kind of very exceptional and you are in this hyperbolic and boring situation because you're out of the spectrum, this matrix here is like this kind of rigid rotation. Like this matrix that you're going here, its limit here has an elliptic matrix here. So this cocycle here that you're aiming at is bounded. When you take a change of coordinates, you don't change the Lyapunov exponent, right? The Lyapunov exponent is something intrinsic and invariant by coordinate change. So if this was, if alpha A is non-uniformly hyperbolic, right? Particularly if it's related to, well, it's kind of in a situation where there is this kind of decay and complicated so on. But in this particular situation, so with positive Lyapunov exponent but not uniformly hyperbolic, this is an obstruction, cannot be almost reducible. Okay, so if the matrix are not are growing exponentially, then it cannot be almost reducible. But there is a kind of a subtler situation here, which is well, now things become more complicated. This won't go. Okay, so here's the basic. So there is an additional obstruction that you can easily check. That I'm saying that things are making everything in analytic sense, so there is some kind of complex extension of everything that I'm saying. So this change of coordinates that you're getting, that you're defining, they are defined in a neighborhood. So you have the circle, and there is some neighborhood here where things are working on, some little epsilon of that you can vary the imaginary part. And if you do this change of coordinates, it's operating in this whole, small perhaps, but a whole complex neighborhood. So in fact, if you are almost reducible and not hyperbolic, implies sub-exponential growth for a small imaginary part. So you get kind of, you can control because you're close to constant in a whole neighborhood. If you are close to constant, the Lyapunov exponent has to be almost 0. So since the Lyapunov exponent is invariant, it was almost 0 originally. And since it's independent on n, it has to be 0 in the whole, for this whole imaginary part, small enough. So you get this restriction, so you get this implication. Okay, it's curious. Then there is a theory that was developed along many years that developed techniques to manipulate the Lyapunov exponent and say interesting things about Lyapunov exponent. It's kind of tricky because let me explain. One of the difficulties is that you'd say I'm interested in Lyapunov exponent equals to 0, for instance. Well, very well. I have a function in an infinite dimensional space because you have, in general, when you allow V to be analytic, you get just depending on your setup on a Banach space of analytic functions and so on, and you have other parameters, but infinite dimensional. But anyway, you have a function. And you can set it equal to 0, so you're solving an equation of this function. You try to understand geometrically, for instance, you get some set with the solutions, and you're interested in one parameter family that's related to the particular operator that you're considering, how it intersects the set of solutions of this equation. And you could try to imagine a geometric approach to this problem by investigating this kind of transversality properties in this infinite dimensional space and so on. Very well, except that this function is extremely irregular. So this function, in the best possible situations, is only half Hilda at most. And usually, whenever things get kind of really interesting, it gets worse, even worse, and you actually don't know very well currently what you get in the critical situations. But anyway, you don't expect it to be better than half Hilda, and solving equation L equals 0 with a irregular function is not going to be, it looks like a hopeless approach. So the geometric approach looks bad. But a few years ago, I developed a technique that allows to work on equations of this, even if L looks very irregular. So somehow there is some kind of hidden structure that's compatible with this kind of irregularity in the traditional sense, but allows you to kind of solve this kind of equation and get some things that can be dealt with geometrically. Anyway, so there is this technology. So talking about Lyapunov exponents and controlling some information about Lyapunov exponents became possible. And this makes it important to say, what does Lyapunov exponent tells
you about your system. And this led to the formulation that actually Lyapunov exponent tells a lot about the system, which is the almost reducibility conjecture. We said that here I needed to say not uniformly hyperbolic, not boring situation. So this is the full statement. So this implies that, so that's what I basically proved here, it's trivial. The opposite implications is what's the subject of this. And, okay, so that was what was important. So the point is, what's the big content of this? On this side, you have some asymptotic information. You're just saying that the matrix don't grow very fast. And it just says what happens very far away. It doesn't suppose that you are near constants. You don't have principal information. It doesn't say that you kind of stay bounded. Just say that if you wait long enough, you start seeing, you cannot be seeing something exponential and through a whole complex neighborhood. And from this, you have to find a change of coordinates that are going to make you get closer and closer to constant. Okay, so this motivation for this, that it could be using the techniques of the almost mature operator, this was verified. So let me just mention, that this kind of thing, sub-exponential growth for small imaginary part, I called subcritical behavior. Because just to mention here, so a theorem, a basic theorem is that if in the case of almost much subcritical, in the other sense, most mature cocycles, let us say, so subcritical means lambda less than 1, are actually subcritical with this sense. So that the definitions were supposed to be compatible. So in the dynamical sense. So that's how you come with the terminology. And this subcritical in this case. So this shows by studying kind of special feature of the almost mature operator, you get that it was in particularly a particular true because subcritical almost mature is exactly the set of parameters, because you can compute exactly the Lyapunov exponent in the spectrum for the ones which you have this behavior that they say here. For lambda equals 1, and that's an important point, you are going to have 0 Lyapunov exponent, but when you go off the real axis and you go to a small imaginary part, it becomes positive. So this can be computed, and it is true. I could write a formula for the almost mature operator. The Lyapunov exponent is equal to log lambda. Max 0 log lambda. So it's 0 when lambda is less than 1. So subcritical is still 0 for lambda equals 1. Then it becomes positive. But for lambda equals 1, it's different. And it's not subcritical in this sense because it is off the real axis, it becomes positive. Anyway, you get this theorem. And I don't have time to certainly to discuss how technology that goes into this theorem, but because I should finish, the only thing that I say is 2 theorems that motivate this. And so the first theorem says that almost reducibility is a nice concept in many sense. So almost reducibility. So reducibility I didn't like because it was there was this kind of subtle arithmetic questions and there were positive measure considerations. But almost reducibility is an open condition. It's stable. If you have something that's almost reducible, you perturb, it's still almost reducible. So this kind of nicer to kind of put your hands on, and then all kinds of theorem becomes nicer to state and more powerful once you have that. If you have almost reducibility also, you can change coordinates and go close to constant. You can apply whatever method you have to deal with close to constant things. So you can apply KEM theorem, for instance. So it's kind of useful. And so this is one important theorem. Another important theorem, that's the part that's not kind of available for some years because just by slowness. This is true. The almost reducibility conjecture has been proved. And then what you do when you put all the theory together, you get this theorem here. That's called the spectral dichotomy. If you take a typical in a specific measure theoretical sense, it's a little bit complicated because it's an infinite dimension. Typical operator H here. So you may vary alpha, and almost every alpha will be, it makes complete sense, but also almost every V. So what does it mean? You have to introduce some measure, some kind of measures of some kind and talk about concepts of prevalence and so on. But there is some kind of well-established notion that can be implemented here. So anyway, for a typical operator that you find, you may have, it's no longer, it's not true in general that you always have one kind of behavior. You can have coexistence of different behaviors, can be proven. What happens that the spectrum, so this is spectrum, is going to break down into pieces. So this, you imagine that those are Cantor sets. There are gaps here. Separating parts. In this part of the spectrum, you are going to have, let's say, subcritical behavior. And then there is a gap. And then there's another part where it's going to be supercritical behavior. Subcritical and so on. There's a theorem that, examples that show that you can have actually many of those parts. I didn't explain what's subcritical and supercritical. So here, it means that you have, let's say, almost reducibility. Because of the theorem, I can just say it like this. And in the supercritical part, you have no uniform hyperbolicity, so post-Lyapunov exponent. And then it alternates finitely many times. Or in other words, you break down your operator into a sum of two parts. So this would be, it's a supercritical operator with localization. And this is a subcritical operator with almost absolute continuous spectrum in transport. So in a sense, and the spectrum of those two operators are disjoint. So the spectrum of H plus. So this is the content of having this kind of space gaps between them. So for the quantitative view of quantum dynamics, then, is that in the general situation, the typical situation is that your particle, if you have a component in the space related to this operator and another component in the space related to this operator, one of the components will kind of move quasi-periodic, so it stays localized. The other component will move away very fast. So it gives essentially a complete description of the dynamics of a typical class of operator. And by putting together all this, and in the end applying this concept of almost reducibility that's necessary to finish the picture. So this is the kind of main theorem in the end. And that's how dynamics get this. And of course, there are many details that you need to put together, reducibility gets into, and so on. But I really need this concept to get kind of a stable thing. This is what gets, I mentioned at some point, the theorem that I had originally with Rafael Krikorian, and that you had just almost every. But so it took like 10 years to get from almost every to this kind of description that would avoid that kind of zero measure set. There is still some exclusion. This exclusion is entirely at the level of, but varying the potential. But for fixed potential, you can discuss all energies, and then you understand the spectrum. Very well.
Thank you very much. It's time for questions. So, are there any questions? Yes. Well, maybe we can pass.
Okay. Działa? No, I have a few questions, but one most important to me is that if we have start with I don't know, more typical quantum mechanical Hamiltonian is minus Laplace operator plus something, and is some obvious way if you have such operator translated to problem relate to this problem as this of L2Z and draft some information on it's a case-to-case study.
So first, the almost mature operator, it arises in physics literature like that. So it's not, it doesn't start from continuum form and then becomes discrete. It arises like this, and it appears in the investigation of quantum Hall effect as it is. So first, it is sometimes the natural thing to consider. Second is there is a class of operators that correspond to what I'm describing, and which have, instead of Z, is the real line. So it should be, let's say, instead of, so here what you have is dynamics on the circle that's underlying, which x goes to x plus alpha, okay? And then you get a discrete dynamical system, and that gives the potential. So what you replace now, you get a dynamical system on the two torus, and you have a translation on the two torus. And now you have but a continuous translation. So you have a differential equation that you move here, and this will correspond to give a potential on the real line by evaluating something. So there is a kind of a continuous version of the theory that I mentioned here. And basically, things are related because if you look at a dynamical systems like this, you can take the Poincare section. Here, you look when the flow comes back, and the dynamics that you get here is exactly here. So you'd have to integrate the differential equation related to that, and you get a new matrix cocycle, which is discrete. And it will be basically the same, except the matrix cocycle will have a SL2R form, but not exactly the one that's written there, but it's still a SL2R cocycle. So things like the almost reducibility conjecture, by solving it for the discrete case, it also implies for the continuous case. So essentially, most of the theory goes through there, but I'm usually, there are some things related to the extent of what I did, it goes through. There are some issues related to the relation between positive Lyapunov exponent and localization that people had not worked so much, but it's something that, so particularly the Bourgain-Goldstein theorem that works this kind of relation, that have not been carried to continuous setting, and I don't know how much of these people don't have, they did the discrete case, and this you cannot reduce immediately from continuous to discrete. But basically, the theory should be more or less the same.
Any more questions? Please. Yeah. Nice.
So what about this operator H whenever we have a given alpha? Yeah? And so what about the description of the class of V for which you know the description of the essential spectrum?
So the spectrum, so you mean non-point spectrum? The spectrum. So basically everything is essential spectrum because the spectrum is a kind of usually a Cantor set, right? So there are no isolated eigenvalues appear in the spectrum. There are very general theorems. So it's very generally what I said. It's a Cantor set. Normally you expect, but it's very difficult to prove. So there are many theorems that say in many situations it is a Cantor set. And there are theorems saying that in most situations it has positive measure, but what's actually to state exactly, I would have to make some statements about precise arithmetic conditions and parameter exclusions that you need to make. But there's a whole theory about that, yes. But basically everything is essential spectrum. This is kind of this type.
Yes. Any more questions?
So you assume that this potential is analytic, and you provide us with only one example with Mathieu, this Mathieu function. So there are some interesting examples for different from other, some other, say, polynomial potentials or something?
So as long as, so there are something. So if you ask for polynomial, you could get some specific formats. They are not as initially as motivated as the almost mature. That is, so you could understand just because they're polynomials. Let me mention that there is some other variation of this that has been studied, but it basically goes from, it's related to almost mature operator, but it gets to SL2C, and it looks at not only near neighbor interaction, but next near neighbor interaction. So get the so-called extended Harper model, and there is a theory that has been carried out recently, but it's not exactly just making but the theory here kind of actually generalized, but not to just taking this model and making the potential polynomial. In most cases, there is not much different. There are some cases where people are studying this, but from the point of view of the general theory, from my point of view, basically, as long as it becomes a general polynomial, it's as good as taking a general analytic function. As getting, you could get below analytic, and then the situation changes substantially. The analysis becomes different, and I should mention that the one difference that's very important is, of kind of results, is that there is an important theorem that's the Burga and Zhytomyskaya theorem, saying that the Lyapunov exponent, which I said that was a regular function and so on, is at least continuous. It plays an important role in the theory. This is a theorem valid in the analytic category. It's false for a smooth category. So you see that there are important differences already at this level.
Questions? Well,
have you or other people considered the case when V is a matricial function? So it means L2 spaces with vector valued functions.
So whole, there are variations that you can construct this, where the matrix that you get are not kind of going to be just 2 by 2, but higher. So that like one normal situation that you get is if you have so-called strip model. So instead of having just a lattice here, you could get several lattices, and you can interact between one Z and another Z. So there is some kind of near neighbor interactions. And when you get this, you're going to get a more complicated symplectic matrix that you're going to make the evolution. So there is theory related to that. There is a kind of course, another direction is to consider like infinitely many copies. So just instead of Z, you get Z2. And then the theory is certainly not as advanced, and the main things that in the end is not kind of, the connection with dynamical systems is not as good as we're discussing here. So don't approach it by dynamical systems. There is its own technology. I should mention as well that there is a generalization of just considering other kinds of dynamics. So some examples are like a Bernoulli case, where instead of having this potential here that I gave by some specific formulation, I could make random potential in each side. So that's another generalization. So this is kind of very easy to understand in the case of one dimension, and then you get very complicated questions when you look at high dimensions. So that there is some famous open problems related to existence of, so there are theorems related to localization for random potentials in high dimensions, but there are conjectures, but no techniques to handle what would be absolute continuous spectrum in that case. But anyway, you are getting out of the scope of dynamics already by that time.
Yes, more questions? Well.
My question is about this singular spectrum. Is any, I don't know, theory to say us about something about how can we localize on the real line this where this singular spectrum really is? But because it's not captured, but I don't know, Lebesgue measure, it must be a quite a strange, at least to my intuition set.
Well, first, this theorem is designed to get rid of this singular continuous spectrum. So this theorem says that up to the exclusion of some v's, you don't get any singular continuous spectrum, because there's only AC spectrum and point spectrum. Now, of course, sometimes it exists. Example is like the critical Mathieu operator is one important case where you are going to have the whole spectrum with a zero measure set has singular continuous spectrum, and then you can ask questions. So this set, we don't understand it exactly. It's expected that in some settings it should be a set of positive house of dimension still, but less than 1. And in another set, maybe it has, well, you know that in some situation it can have 0 house of dimension, I think. I think that there are some theories in this direction. Now, so there exists this set. Now, but one more thing that you understand a little bit better, and for me is kind of less interesting to understand the critical point, is the case where, let's say, you take the almost Mathieu operator, and I say, let's suppose that you take now a supercritical situation, and you make alpha be Liouville, very Liouville. So what I said was, when I'm talking about non-uniform hyperbolism, was mostly designed to describe the Diophantine case. But there is a zero measure set of alpha where alpha is almost rational. If you have an operator with rational alpha, so the sequence V and alpha would repeat, it's very easy to say that then you get AC spectrum. Now, if the sequence almost repeat with very much precision, you're not going to have AC spectrum, but you're not going to have point spectrum either. It will get mixed, and then you get singular continuous spectrum. So there is this theorem that says, and there is a whole theorem of Berry-Simon and so on related to this kind of events. But in this particular case, there is so-called Gordon lemma. And if you take very Liouville alpha, you have pure singular continuous spectrum. And in this case, the set, it's still a positive measure set. So it's still, the formula that I wrote is still valid. So you have 4 minus 4 lambda bigger than 1 measure for the spectrum. And you have a spectral measure supported there that's singular. But the support of a measure can be, the topological support of a measure can have positive measure, Lebesgue measure, even if the measure is not absolute continuous. There's nothing. So that's, in this case, that's what happens. So I'm giving you 2 different situations. In one, related to when the source of singular continuous spectrum is related to arithmetics. You get something that's spread out over a positive measure, but it's kind of, in terms of measure, is concentrated. And in the situation that arises in the almost Mathieu operator, that is pretty rare, so there are no other examples where it appears, so that we know of. It appears really in a concentrated set, which has 0 measure and probably less than 1 house of dimension.
Yes. Are there any more questions? Well, you see the suggestion. So, thank you very much for the lecture. Thank you very much for your attention.